Hello. In the previous lecture we discussed about ALU and shifters and rotators, and in this video we will see multiplication and division. So multiplication and division, both of these we are implementing using algorithms which are inspired by how we manually do multiplication and division, right? So consider this multiplication of these two 4-bit numbers, A3, A2, A1, A0, which is A, and B3, B2, B1, B0, which is B, right? So how do we multiply these two? First we multiply B0 and A0, we write it here. Then we multiply B0 A1, we write it here. Then B0 A2, write it here. B0 A3, write it here. Then we do the same with B1, B1 A0, B1 A1, B2 A2, and B2 A3, right? Sorry, B1 A2 and B1 A3. Similarly for B2, and every time we are doing this, we are shifting them by 1 to the left. And finally, what do? We add them, right? We add this, we add this, we add this, we add this. So basically, what are we doing? We are adding. These are actually bits. These are single bits. A0, each bit can be 0 or 1. So multiplying them means we are ANDing them. We are doing AND operations to the two bits. So A0 and B0, A1 and B0, A2 and B0, so on and so forth. Addition is additionally proper addition we have to do. So how do we do this? We take this directly, we add these two terms A1 B0 added to A0 B1. This will be 1 bit. These P0 P1, these are all single bits. Okay, then A2 and B0 plus A1 and B1 plus A0 and B2. This will be added, and this will be added along with the carry which is coming from here. Okay. Similarly, these will be added along with the carry which is coming from here. These will be added along with the carry which is coming from here. It's like regular mathematics, how we do regular arithmetic. This is it. That's it. This is the simple logic behind a multiplication. So how do we implement this? We implement this using AND gates and adders. Those are all required, AND gates and adders. That's it. So you can refer to diagram 526 in the textbook to see a proper diagram. It is a little bit big and cumbersome, that's why I am not representing it here. Anyway, it is available in the textbook. There is one more method of multiplication called a shift and add method. This one is faster, right? This one is fast because it requires a lot of hardware. But this shift and add multiplication technique, which is efficient with regards to hardware complexity. It is implemented using an adder and shift registers. So it is efficient with regards to hardware complexity, but it is slow. But this is much faster, and this is costly when it comes to hardware. So anyway, shift and add method is not in your syllabus, but I strongly urge you to go through that at least once, so you will get a sense of it. Okay, let's move on to division now. Considering division, any division of two numbers A by B is basically what it is. It is a quotient plus a remainder. So A is the dividend, B is the divisor, Q is the quotient, and R is the remainder. Here also we are actually going to implement a simple long division method which you learned in school. We are just formalizing it into an algorithm so that it can be implemented in hardware and other computational purposes, right? So just some terminologies. This R and R bar are not the same. Partial R bar, we will be calling it as partial remainder, and R we will call as remainder. Then this I notation, A of I is ith bit of the dividend, and Q of I is qth bit of the quotient, right? B is the divisor, D is the difference between remainder and B. We will come to that. Okay. So one thing I have to say before proceeding, moving on, is that this is one version of this particular algorithm. There are other versions of this algorithm in which R bar is initialized using A. So then there will be slight changes in the algorithm, but essentially it is the same. So the logic is the same. So there will be slight changes in implementation, but logic is the same, and I am using this particular version because I felt this is the easiest one to understand. Now moving on. Okay, let's go through the algorithm once. So R bar is initialized to 0. Then we are taking one index as I, and we will be implementing this whole loop for n minus 1 to 0. That is basically n loops. We will be repeating this n times. Okay, R equal to, this notation is R bar shifted to the left by 1. Okay, remember left shifting, this is left shift R bar by 1, and this is, it is then appended with AI, right? Or the last bit is added to AI. AI will be a single bit, right? It is the ith bit. For say second, if it is a second iteration, then AI will be the A2. Then what is happening here? R bar is shifted to left by 1, and the last place is being added with AI. This is not actually added, it is appended, right? If AI is 1, then the last bit of this R bar will become, this R will become 1. You will understand it better when you see, when we look at the example. Okay, then we find this difference between R and B. B is the divisor, and we do a comparison whether D is less than 0, that is whether R is less than B. That is a comparison that we are doing. And for one case, if R is less than B, then there is quotient will be 0. If R is greater than B, then quotient will be 1, and there will be slight changes in the remainder also, and we will proceed. Okay, this is done for n times. So let's see with an example. We'll see example in two ways: this long division method, this tabular method, and we will compare it with the algorithm as we move forward. Okay, for here 4 bits are 7 divided by 2, so 0 1 1 1 divided by 0 1 0. Why is there a 0 in the front? Because this is a 2's complement notation, and unless there is a 0 in the front, this will be a negative number and the value will be changed. So there should be a 0 to denote it as a positive number. So 0 1 1 1 divided by 0 1 0. So again, A is 7 0 1 1, B is 2 0 1 0, right? We write like the long division method. So for the first run, R equal to 0, right? A is equal to, here I am always I am writing the whole A, but I am underlined the ith bit for the current looping. So here AI is 0. Okay, so for the first loop, and I equal to 3 here. So I equal to 3, R equal to R bar left shifted by 1, means R bar is R bar 0 0 0 0 left shifted by 1 is again 0 0 0 0, and AI is appended to the, or the last bit of Ri is replaced with AI. Here there is no change because all are zeros, so R is also 0 here. Now we have our R. So that is what is happening here. Here we initialized our R to 0, and we are appending this value to that one, right? and we compare. Now what do we do? We take D equal to R minus B. Now we compare these two. Is R less than B? Right, that is the question we are asking here. Is R less than B? Here, yes, R is less than B. So what happens if R is less than B? Qi is 0. Here, that is the condition. Qi is 0. And if Qi is 0, that is, we have written it here. Also, R bar equal to R. R bar for the next iteration equal to R. Here we have R here. So R bar for the next iteration will be R. Remember, the way we got this 0 and this 0 is different. Here it is the initial condition, and here it is coming from this R. Okay. Now the next one, I equal to 2. Again we do the same thing. We left shift R bar by 1. Left shift R bar by 1, and we append AI. Here AI is 1. So we left shifted 0 0 0 0 left to by 1, and then we appended the ith bit of A. Here it is 1. So 0 0 0 0 becomes 0 0 0 1. So here it is the same thing we are happening. We are just pulling down this next bit here. So 0 becomes 0 1. Now again, what do we do? D equal to R minus B. We are comparing this R to this B. So is 0 1 so is 0 1 greater than this one B? No, right? So again this condition is coming. So Qi equal to 0 again, R bar equal to R. So here you will get a better idea. Here R bar for the next round is this one. So 0 0 0 1 is coming here. So we come to the third I equal to 1 condition. So here again what do? We left shift R bar by 1 and we append this one AI. So that is what is happening. We are pulling down this one here. So 0 1 1 for I equal to 1. This is the one. R equal to 0 1 1, and if we compare 0 1 1 with 0 1 0, now we have the else condition, which is R is greater than B, greater than or equal to B, right? R is greater than or equal to B. Then what happens? Quotient equal to this bit of Qi equal to 1, that we are writing here, right? Again we'll go through this once more. For I equal to 1, R equal to 0 0 0 1 coming from here, and AI equal to 1. So we left shift R bar by 1 and we append this 1 here. So R becomes 0 1 1. That is what is happening here. We are pulling down this 1 from here. So it becomes R becomes 0 1 1. R becomes 0 1 1. And we are comparing it with B, and yes, R is greater than B, so one quotient Qi is 1 here, right? Okay, Qi is 1, right? Qi is 1. So finally we have a 1 in the quotient. Now Qi is 1, also R bar equal to the difference. So what is the difference here? 0 1 0 1 1 minus 0 1. So 0 1 is the difference here. That is how this 0 0 0 1 came here. Okay, this 0 0 0 1 came from here. This 0 0 0 1 came from this 0 1 1 minus 0 1 0. So 0 1, again R bar is left shifted by 1 and AI is appended. So 0 0 0 1 becomes 0 0 1 1. So here 0 1 becomes 0 1 1. We take the last bit down. Again what do? We compare it with this one B. Again in the last case it is greater than B. So what is the thing? Qi is equal to 1 and R bar equal to the difference bit, that is 0 1 1 minus 0 1 0, that is 1, right? Okay, now I equal to 0. This loop was for I equal to n minus 1 to 0. Now that I equal to 0 is done, we terminate the execution of the loop, and the last condition is that r equal to r bar, right? R equal to r bar, and here our r bar is 1, so we put r equal to r bar. So r equal to r bar equal to 0 0 0 1, and the quotient equal to 0 0 1 1. That is what we got here. And 7 divided by 2 is 3, and there will be a remainder of 1. So this is how we implement, this is the basic algorithm that is used to implement division in hardware. And there are not multiple versions, there may be 1 or 2 other versions of the same algorithm. There might be slight changes, but the logic is always the same. This one is the one that I found easier to understand, so please go through it, and always try to do it with an example so that you will have a better understanding, and try to do other examples, not just this one. Try to do new examples. And the schematic diagram of implementation of the algorithm using hardware, it is given in the textbook in image 5 to 7. Okay, so by this we conclude our lectures on digital fundamentals, and from the next lecture onwards we will go into the microarchitecture part. Thank you.